Welcome back to Breaking Banks. I'm your host, Brett King. We are, at this point in the show, we're going to introduce Stephen Wolfram. Now, for those of you that know about Silicon Valley, Stephen is a bit of a legend in the computing community. He's been responsible for many incredible innovations in the space. He's a physicist. He's an author. He hails originally from Britain, and so I share that in common with him in that I have dual British passport. So today we're going to be talking to him about AI, the future, and how things will change soon and far away. So, Stephen, welcome to Breaking Banks. Hey, so tell me, first of all, the first question I have for you is, what's your first recollection of computing technology and your involvement in computers?
In my life, the first computer I met was a mainframe when I was about 10 years old.
Yeah, in your life.
Yeah, that was then I started programming computers when I was about 12.
There you go.
The first computer I used was a thing that I'll be amazed if anybody listening to this show has ever heard of, a thing called an Elliott 903, which was a British computer about the size of a large desk, programmed with paper tape, stuff like that. I started programming it because I was at that time about 13 years old, and I was really interested in physics, and to do physics, you kind of need to do things like mathematical calculations, and I wasn't so keen on those, and I thought, gosh, maybe I can just automate those things and get a computer to do them for me, and that was kind of how I ended up starting to use computers.
So, hey, have you heard of a VIC-20?
Sure.
So, Elon Musk and I share something in common, is we both learned to code on a VIC-20 microcomputer.
Uh-huh.
So I basic, but you guys have been working. I was just reading some research in prep for the discussion today, and you guys have been working on a computer language at Wolfram Research. Well, you've been working on it personally for 30 years. Can you talk about that language you've been working on?
Sure. Yeah. Well, so my company Wolfram Research is now 31 years old, and the thing that's sort of the trunk of our development is what we now call Wolfram Language, and there have been sort of two big things that people have seen that have come out of that. One is Mathematica, which first came out about 29 years ago, and the other is Wolfram Alpha, which came out about 8 years ago. So Mathematica is sort of the thing that allowed people doing technical computation to actually start, the people who were really thinking about doing it, like physicists, mathematicians, economists, other people, to actually start doing their computing themselves rather than sort of relegating it to programmers to get it done. Mathematica, well, over the years, I guess it's pretty universally used in the quant hedge funds and places like that. Traditionally, it's been used mostly on the research and development side. Recently, it's started to be used a bunch more on the production side. But Mathematica it's kind of very, very widely used in the world. For lots of things have been invented and discovered with it, and it happens to be kind of the tool that gets used when people want to figure out new stuff, and that turns out to be something that's pretty important for quant hedge funds and so on, which is why it's very widely used there. Wolfram Alpha is kind of a more consumer product, and it came out, as I said, about 8 years ago in 2009, and it's a thing that you find on the web, and millions of people use it every day to answer questions. So you go from natural language question to sort of generated report, and it's the thing that, for example, powers the knowledge component of Siri, Apple's intelligent assistant, things like that. It's something that knows, its goal is to know a lot about the world, so you can ask it questions, you can ask it all kinds of quant finance questions if you want to. People are surprised that you can just go to wolframalpha.com and start asking all kinds of, Greeks of stocks and things like this. So that's sort of another thing that came out of Wolfram Language. The sort of the trunk of this tree is our Wolfram Language system. Kind of the idea of Wolfram Language is to make a computer language which kind of knows as much as possible. Typically, when one builds computer languages, in fact, pretty much every other computer language that people have built, whether it's C or Java or Python or whatever else, the idea is to have a fairly small language and then to maybe have libraries that different people will build to do different particular kinds of things. My idea with Wolfram Language was a much more ambitious, perhaps crazy thing, which is to build as much knowledge about computation and about the world as possible right into the language. So, for example, in Wolfram Language, it will know, it knows as an intrinsic part of the language how to, solve a differential equation or do a combinatorial optimization problem. It also knows a lot of facts about the world, whether it's geographic data or financial data or weather data or chemical data, all these kinds of things. And the goal has been to kind of curate all this knowledge about the world to be able to, we've licensed data from all these primary sources of data, and we've been steadily sort of collecting the world's largest collection of computable curated data that our language can operate on. So kind of the goal of Wolfram Language is to provide a precise symbolic language that allows one to compute things about the world, not just abstract things, but things where one intrinsically knows, it will intrinsically know currency conversion rates. It'll intrinsically know locations of companies. It'll intrinsically know all those kinds of things, and be able to compute from that. And that's and so this has been
so when you,
as I say, the two most visible spin-offs of that have been Mathematica and Wolfram Alpha. The thing that's happened in the last couple of years is sort of the emergence of Wolfram Language on its own as a force for developing all sorts of software and applications and so on.
So when you ask Siri, tell me what planes are overhead, that's coming from Wolfram Alpha, isn't it?
Yes. Things like all sorts of things like that, and I mean, what we're doing, sort of distinct from something like web search. If you do web search, you're basically saying, did somebody write down the answer to this question somewhere on the web? What Wolfram Alpha is doing is it's saying, can we compute the answer to this question from the knowledge that we have in the system? And typically that process of computing things is a mixture of some source of raw data, like let's say, what's the GDP of Italy divided by Germany? We have to, there are several steps to being able to answer that. One is to understand the natural language question. Another is to know that data, and another is to be able to do the computation on that data. In that particular case, the only thing that will be tricky is there are probably two time series of those GDPs, and you have to be able to divide time series where even though the points in the time series may not be lined up and so on. So those are that's I mean it's a pretty complex thing. Much more it's kind of the most ambitious effort that people have tried to make in sort of providing computational knowledge. And we've worked on many thousands of domains of knowledge, trying to understand the linguistics, the data, and the computations that are needed to answer questions in those domains. I mean, the thing that you see in something like Siri is the public version of Wolfram Alpha operating on public data. Right. There's also a quite different version of Wolfram Alpha, which is the private custom versions of Wolfram Alpha that exist in a bunch of large companies now. I mean, we've been developing, particularly in the last few years, a really very rapidly growing business in taking the Wolfram Alpha technology stack and applying it not just to public data that's accessible to anybody, but to the internal proprietary data of companies, whether that's in financial companies or retail companies or healthcare companies, and being able to do things where one is typically, the most interesting cases are usually combining the internal proprietary data of those companies with public data that we have, whether it's saying, if you say, what are sales like in such and such a place? Well, that's internal data to know what those sales numbers are. It's public data to know socioeconomic.
How much data are you guys consuming on a daily basis?
It's an interesting question. I mean, I think in terms of sort of the raw computable numbers, it's at this point we've accumulated some number of tens of terabytes. So I think on a daily basis we're getting all the financial feeds, all the where the planes are everywhere in the world, all the earthquake feeds, all the weather feeds, all this kind of thing. Don't actually know what the number of bits coming into our data centers is per per day, but it's certainly in the gigabyte range. And the challenge is to take all those different kinds of data and make them really computable. So it's not just some random number that's coming in. It's, okay, that's a wind speed at this geolocation in these units, and we can compute with it in this way to follow, the vector field of the wind to work out this or that thing. That's really the place where there's a lot of interesting and challenging issues, and it's been really the process of making a consistent language that covers sort of all these different kinds of things in the world. It's a wonderful and fascinating intellectual project that also happens to be really valuable and useful to a lot of people.
Absolutely. All right, well, listen, Stephen, let's just take a quick break, and then after the break, I want to get into AI and how we'll frame some of the legal parameters that AIs will have to deal with in sort of coding human laws into AI.
Great.
All right, we'll be back after this quick break. Thanks. Interviewing the one and only Silicon Valley computing legend Stephen Wolfram, talking about Wolfram Alpha and other great tech that comes out of Wolfram Research. So, Stephen, in terms of the framing the problem of data and synthesis of data, AIs are going to be very dependent on this, but also, the whole problem of ethics and legal coding. How are we going to get machines to learn how to conduct themselves with sort of human ethical coding or the legal frameworks that we have in, for example, road laws? How do we encode that into AI in the future?
Right. I mean, the general question, how are you going to tell the AIs what to do, so to speak?
Sure.
And in a sense, this is part of a long arc of history of how automation has worked in the world. And I think the thing we have to understand, the goal of somebody like me in developing technology is to have it be the case that humans can kind of state what their goals are, and then the technology we've built will, as automatically as possible, try to achieve those goals. So, for example, in Wolfram Language, the idea is you are defining in the language what you want to have happen, and then the innards of the language are working out which particular algorithms, computations, whatever else should get done to make that thing happen. So the real pressure is on figuring out how are you going to specify those goals. And to specify those goals, you need some kind of language which can define, which can describe things that humans want to see happen. And those things that humans want to see happen typically involve things about the real world. They don't just involve some kind of abstract computational kinds of ideas. They involve things like, I want to buy this particular stock. I want to do something. I want to go to this particular place. These kinds of things. It involves knowledge of the real world. So it's the thing one has to then do is to try to figure out how do you make a bridge between sort of what we humans can think about and talk about and what our computers and AIs know about.
Yeah.
And that's, in a sense, the role of a computer language, a role of our Wolfram language, for example, is to provide that bridge, to provide something where humans can express what they want in a precise way, and then the machines can understand that language and be able to execute those things or try to achieve those goals. So a typical way that humans right now would state some complicated set of goals, one example of a model for that is legal contracts. And a legal contract, one might just say, well, we'll just write them in pure English, but we know people have sort of evolved to write legal contracts in this sort of slightly more precise form of English that's, legalese.
Legalese, yeah.
Legalese is kind of one step towards writing a contract in code, writing a contract in some absolutely precise symbolic language that can then be understood by other humans and by computers. And so one of the things I've been interested in is how do we define things that should happen in the world in code? Actually, it's sort of an old problem. I mean, this is back in the prehistory of computing. People like Leibniz in the late 1600s. His original idea was that he wanted to figure out a way to get rid of all those human lawyers and human arguments. He just wanted to have a machine, a sort of universal logical calculator that could answer any legal question. Well, he didn't succeed. He was arguably 300 years too early in the sort of progress of technology, and actually surprisingly little has been done in the intervening 300 years.
They still admire his goal in terms of what he was trying.
His goal is absolutely alive and well. The issue is that the sort of the underlying technology and so on hasn't existed, but we are now really close. So, for example, there's pieces we don't yet have, but we are within kind of striking distance of being able to define things that we want in typical contracts in code. Now, there are pieces to that are sort of added by some of the modern machine learning capabilities that we're starting to have. I mean, if you say, for example, I don't know, let's say I want to get 30 pounds of grade A apples or something. If there are grade A apples, I'm not sure if there are, but what is a grade A apple? Well, it's probably something that's defined by the U.S. Department of Agriculture to be an apple that doesn't have too many blemishes and is roughly this color, et cetera, et cetera, et cetera. In the past, that definition is something you kind of had to execute using a human inspector, picking up the apple and saying, yeah, that looks okay. Now we can expect to have a machine vision system that can be taught, this is a grade A apple, this is a grade B apple, and for example, both parties to a contract can just agree it's this machine learning classifier that's going to decide what kind of apples we're talking about, and that then becomes part of this computable contract to say that there are the apples will be defined by things that the machine vision system says are grade A or whatever else. And so that's a way that we're kind of able to take what would normally be a sort of pure human judgment part of something like a contract and make it be computable. I mean, the thing to understand...
In terms of, we talk about this as a problem for laws, but I'm more interested in how we encode ethics. I mean, you've heard the trolley problem, of course, with the self-driving car. It gets done to death. But, how are we going to be able to instantiate ethics and ethics in code when we can't even agree on a society on a code of ethics?
Yeah, well, that's, if I think we'll have the technology to encode what we want the AIs to do. Figuring out what it is we want the AIs to do is a separate problem. And I think one of the things to understand is that, as we think about these kind of smart contracts and so on, one of the most important ones that we have to think about is what does the smart contract with the AIs look like, so to speak. And, back in the day, people were sort of talking about, Asimov's laws of robotics, law number one, don't hurt the humans and so on. I don't think that there is going to be any way to have a sort of a simple sort of mathematical theorem-like version of this is what we want the AIs globally to do. And I think what we're going to end up with is something much more like human laws, where we have to sort of build these separate sort of AI constitutions that cover lots of different cases and that gradually evolve over time. I mean, the issue of evolving over time is a very, very tricky one because increasingly we will cede control of many kinds of things to AIs because they're frankly better than humans at making sort of repeated judgment calls. Once we've done that, the question of how we then say, okay, but we want to be able to change that constitution a bit, that's a tricky thing. I think the challenge right now, as I see it, is sort of step number one is solve the technology problem of being able to specify the goals for AI. Step number two, what do we humans actually want? And it's kind of a more than anything, it's a very intense mirror on kind of what we really think humanity is about to try to figure out what it is we want the AIs to do.
Maybe, this is a really interesting challenge. When you hear Musk and Stephen Hawking and others talking about these challenges, if you're going to try and encode machines that are going to respond ethically in the same way the best of us as humans would be, it occurs to me that we sort of need to sort of create some, ethical boards or think tanks that can actually define what it is. It should be the benchmark of ethics for us to code.
Interesting problem. I mean, like one of the things that one might say is, okay, machines, do it like the humans do it. Go watch all the YouTube videos and go conduct yourselves just as what you see in those videos. Probably not the best of ideas. Similarly, the kind of have the experts figure out what ethics should be like. It's interesting. Because we've done a lot of curation of lots of kinds of data in the world, whether it's some data about all the battles in history, or whether it's data about all the kinds of chemicals that people have synthesized. One of the things that I was curious about is, can we sort of curate the ethical systems of the world? What a mess! It's really. I think what will actually happen.
Surprise if you can figure that one out, dude.
Yes.
One thing that comes up in our world is there's been a debate around online lending and whether AI really makes sense for making online lending decisions, because up till now, you've had a lot of lenders that use software to make their lending decisions. They take in the credit score, they take in the income, they take in all the pieces of data that are used to make a decision, and they apply all these rules that the bank's policy or the lender's policy that they've set up. But the thinking is that if you let an AI engine make these decisions, it's going to learn over time and kind of make up its own rules or make up its own playbook, and that along the way, people could be dropped out. People who live in certain neighborhoods, or people of a certain gender, or people, the software could start to make its own conclusions about who's really creditworthy and who isn't, that might be a little different from what the lender intended. And then on the other hand, you have online lenders that use AI, and they say software makes a decision much better than a human, because when you walk into a bank, the human is going to look you up and down and see if you look like someone they know, if you remind them of someone they know. So the question is, what do you think? Do you think there is a danger of the software running amok, or do you think computers, could make better decisions than people in a situation like that?
It's interesting because our technology, Wolfram Language, is pretty widely used by these online lending folks as ultimately the decisions are getting made by little pieces of Wolfram Language code, and nowadays increasingly using our machine learning stack.
So you're responsible.
So we're involved in some way. Of course, we're just selling the tools. We don't know exactly what people do with them. But in terms of this is exactly the type of thing that one has to think about. If you say, "Gosh, we want to implement the following kind of policy about how we treat different different folks with different backgrounds or whatever else." If you can define what that policy is in some computable way, then it's something that you can build into the system. If you can't describe it, if you're just like, kind of be nice or something, that doesn't really work. So the pressure again gets put on, can one have a language which can talk about the real world, so it can talk about things like, ethnicities, income brackets, zip codes, things like this. And if one can talk about those things, then one has the chance to be able to write down what it is one wants to have happen, and then one can get that executed. In terms of whether, sort of left to its own devices, a supervised learning system that basically just says, here's the raw data, now see whether the loans got paid back or not. That if your definition, if what you want to have happen in the world is to make sure the loans get paid back, then yes, that system will be will undoubtedly be, almost by definition, the most unbiased way to find out, given the input data, will the loans get paid back? But if the story of what you want is not just will the loans get paid back, but also will you treat different kinds of people in the same way and so on, then that's what you have to define with some kind of language. And that's why you need something. When people talk about, machine learning and AI, actually, I should distinguish those two things, because what people usually mean these days by, machine learning is typically neural networks, deep learning, and so on. We happen to have very lovely technology for doing that stuff and be very involved in that. but there's a certain set of things that can be done with that, and it isn't everything that computers or AI can do. It's a certain set of particular kinds of ways of essentially modeling the world, where you say, here's a bunch of ways that the world is right now. Okay, neural net, find something which kind of interpolates the way that the pieces of the world that you can see, and figure out for the next person who walks in, how do they fit into all the people you've seen before. That's something that can be readily done with things like neural net technology. If you want to be able to say, oh, and by the way, I want you to make sure that you give equal weight to this feature and that feature and so on, then that's something for which you need some kind of precise symbolic language. That's not something where you just throw the data in and expect the neural net to figure it all out for you.
So, Stephen, we've only got a few minutes left, so I wanted to ask you this question as we close. You spend a lot of time working with some of these leading organizations out in Silicon Valley. Looking over the next 5-10 years, what most excites you?
Well, I think the thing that computation and computational knowledge is something that we have a lot of capabilities now. It is gradually becoming more ubiquitous. We're gradually going to be able to sort of take for granted a higher level of computational knowledge and sophistication in the things we do. It will not be the case that your computer just has an operating system that operates the computer, so to speak. It will be the case that your computer intrinsically knows lots of things, and you can automatically compute lots of things from it. And for me, as I look at things I've done in my life, I've kind of alternated between doing basic science and technology and business and so on. What sort of happened is that every time I have sort of better tools or a better level of conceptual understanding, I'm sort of able to go further. And I think that's something that we're going to see the next level of kind of what is made possible by computational knowledge. There are going to be a lot of very interesting things enabled in the world. I mean, I think we're seeing that right now with Wolfram Language. There's a whole raft of startups and so on that are coming online that are based on the technology stack that we've built, that are able to do things that kind of seemed magic before, and now they're practical and doable, and we'll see a bunch more of these steps being taken that will lead to things that I think probably the thing that I always find most exciting is the things that I don't expect to see. The things that, when I have thought about, okay, what's coming in the future, it's like I can see the pieces coming together, but I can't see the consequences of it. And I think those will be for me, the most exciting things. And there are lots of them that are I think going to arrive as we kind of reach the next level of automation in what we can do with computers.
Well, thank you very much, Stephen, for your time today. It's been mind-blowing, as usual. And so if you guys want to know more about what Stephen's doing, check out Wolfram Research and, of course, Wolfram Alpha, which is the platform he is talking about. But, Stephen, once again, thank you for joining the show today. And also thanks to Ben Robinson, Duana at Terminos, and to Penny Crosman, our regular support anchor host from there. If you guys are listening to the show, make sure you can go to breakingbanks.com and check out our previous episodes. Go to Google Play, SoundCloud, iTunes. Leave us a review whenever you can. And also don't forget to subscribe to Sam Moore's podcast, FinTech 5, as well. And stay in touch with us for news on Money 2020 and what's happening next. Thanks again, Stephen, and have a great week. What's left of it.
Thanks. Bye-bye.
That's it for the show today, guys. We'll see you again next week. Bye.
You've been listening to Breaking Banks with host Brett King. Please be sure to join us again next Thursday at noon Pacific Time, 3 p.m. Eastern Time for more of the latest in FinTech news.